In our previous video, we discussed sequences and what it means for a sequence to converge. Namely, it means that every subsequent term approaches a finite value. So for example, if we looked at something like the series a sub n is equal to 1 over n, we see that as n approaches infinity, these terms are going to approach 0. Or in other words, a sub n is going to approach a finite value, in this case, of 0. So we see the subsequent terms are going to settle in on a finite value. Therefore, we would say that 1 over n, this sequence converges. Now we're talking about series. And a series is simply a sum of a sequence. It just means that instead of simply having a list of numbers, we are adding up all the terms of our sequence. And we should have discussed this a bit in pre-calculus, but our primary focus in this course is to actually work with infinite series here. And an infinite series, as hopefully you are familiar with by now, is simply can simply be notated using sigma notation, right? We first discussed this when we talked about integrals, which are effectively the sum of a bunch of really small partitions. So we would be able to state here this series, this particular series, can be written in this sigma notation, where again, n equals 0 representing our lower index and our upper index being infinity. Now, there are two different types of ways that we can look at series, or two types of behaviors we can examine here. One is a divergent series, and that's simply a series that does not have a finite sum when an infinite number of terms are added together. So we're adding and adding and adding an infinite number of terms in our series. And if it doesn't ever look like that sum is going to ever settle in on a finite value, in other words, it keeps getting larger or it keeps getting smaller, we would call that a divergent series. However, when a series does have a finite sum, when infinitely many terms are added together, we call that a convergent series. So let's try to come up with two different examples of this. And I encourage you right now to pause the video right now and just think to yourself and ask, what would a divergent series look like? What would a convergent series look like? So pause the video and think about that. Well, hopefully you've had a moment to think about that for a bit. So a classic example of a divergent series would be something like a lower index starting at 0, and it could be 1, 2, it doesn't really matter. Something like this. This would be a pretty clear example of a divergent series. Or you know what, let's make it even easier. Let's just say something like that. That would be a divergent series, because what does a sub n look like here? A sub n looks like it would just be 1 plus 2 plus 3, and I should probably make this 1 here just so we can stay consistent with what I'm writing out, plus 4. So here's my series. And as n approaches infinity, we're just going to continue to add a number of terms that approach infinity. So in this case, this series does not appear to have a sum that settles in or gets close to a finite numeric value. Therefore, we would say that this series is divergent. Well, what about a convergent series? What might that look like? Well, I'll set up the sigma notation again. This time n is equal, let's go with 1 just to be easy. So something like this here was probably one of the earliest examples of a convergent series that we saw. Because something like this would look like, well, when n is equal to 1, I would have 1/2. When n is equal to 2, I would have 1/4. When n is equal to 3, I'd have 1/8, 1/16, 1 over 32, and so on. Now, right now, it may seem like our sum is getting larger and larger, but really think to yourself, what happens as n approaches infinity? As n approaches infinity, we're going to get such a large denominator that effectively we are adding 0 over time. So what we would see here is that this sum gets closer and closer, you probably figure it out, it gets closer and closer to a convergent value, okay? We would say that this series is, we call this series convergent, okay? Now, there are a number of tests that we will explore in this course to determine convergence of a series. In fact, we'll probably spend a good chunk of Chapter 8 discussing these tests. There is, however, a divergence test, and it's one of the first tests we'll learn in this course. And this test for divergence is essentially just rooted in the question, if we add an infinite number of terms, what has to happen? What has to be a condition in for the terms as n approaches infinity if this series could even possibly, not even definitively, but for this series to even have a chance at converging? What has to happen to those terms? In other words, what has to be happening here to a sub n as n approaches infinity in order for this to happen? Well, the answer is a sub n has to approach 0. How can we state that mathematically? We would say that the limit as n approaches infinity of a sub n would have to be equal to 0, would have to approach 0 in order for this to ever have a chance. The nth term divergence says, all right, well, let's not get too ahead of ourselves. Let's just make sure we establish what we know for certain. That if this here is not equal to 0, then we know for certain that this series will diverge. So again, what we call the nth term test, or what I'll often refer to as NTT for short, NTT states that this particular series, written of a sub n, this series will diverge if the limit of a sub n is not equal to 0. And intuitively, this makes sense, right? That if we're adding terms, if a sub n is going to produce terms that are not 0, then our sum is going to continue to grow or continue to go the opposite way. It's going to continue to add negative values. But just really think about that logic there, that if a sub n is not equal to 0, if we're not adding if we are adding terms that are not effectively 0, like again, looking at what we have here, then we know for certain that this series has to diverge. Now, this is where we have to be incredibly careful, because students will, or not just students, anyone might look at this test and then assume that the converse has to be true. But the converse is not true. The converse says that the test is inconclusive when the limit of a sub n is equal to 0. So just because a sub n, the limit of a sub n, I should say, is equal to 0, does not mean that your series converges. It is simply inconclusive, and I cannot emphasize that enough. Okay, and because and students will often ask me, what's an example of that? What's an example of something where the limit of a sub n is equal to 0, but it actually diverges? Well, probably the most classic example of this is the following series. So this is going to be one of the things that might kind of rock your socks early on, because you look at this and you say, all right, wait a minute, as n approaches infinity, you're adding terms that are effectively 0. So this series must converge. But this series, in fact, diverges. What? This series actually diverges. This is what's known as a harmonic series. And again, we will talk about this more later when we talk about these convergence tests, but this is what's known as a harmonic series, which actually diverges. So I only bring that up now just to really remind you or emphasize that just because the limit of a sub n is equal to 0 does not guarantee its convergence. All NTT states is, well, if the limit of our series is not equal to 0, then we can say for certain that this series will diverge. So we've got a couple of examples here where we are using NTT to determine whether or not the series will diverge. Again, we're not determining whether or not it converges, but whether or not it diverges. So let's look at a couple of things here. Let's start by applying NTT. We're going to say, let's look at the limit of a sub n as n approaches infinity of 2n over 3n plus 1. Well, let's think about what's going on here. I can rewrite this, if this helps at all, kind of see the limit. If I divide everything by n, this would be the same thing as the following. So divide both the numerator and all the terms in the denominator by n. And we would say here that this is equal to 2/3. So what is the limit? the limit here, and I'll do this part in a different color, is equal to 2/3. This is not equal to 0. Therefore, that means we are adding terms as n approaches infinity. We are adding terms that are effectively 2/3. It's like we're adding 2/3 over and over and over again. There was no way that this series would converge. So for certain, we can say that this series diverges. Okay? All right, let's try another example now. Let's look at this one here. And again, we're going to look at the limit of a sub n here as n approaches infinity. That's how we're going to apply NTT. And maybe splitting this up into two different fractions might help us see this easier. If I divide both terms in the numerator by n cubed, I get 1 over n plus 2 over n cubed. Well, what happens as n approaches infinity? Well, this term gets close to 0. This term effectively is equal to 0. So we would say the limit of this is indeed equal to 0. And so this does not pass NTT. It does not pass that test. So we cannot say that it diverges. So again, does that mean it converges? No. This test is inconclusive here. So we don't know whether or not this series converges or actually diverges. It could still diverge. All we can say is that NTT doesn't tell us anything about its divergence. It doesn't say anything about its convergence, but it also does not tell us anything about whether or not it diverges. Spoiler, just to give you a heads up, this one actually diverges. This is actually a divergent series, but that's for another day. All right. Number 3, again, I would pause, have you encourage you to pause this video, think about this for a bit, and if you're back, we could write the following statement, that this would be 4 minus 1 over n squared. This here is equal to 4, which again is not equal to 0, so therefore this series diverges. So hopefully this lesson helps give you an understanding of what it means for a series to diverge or converge, and gives you a better understanding of the nth term test for divergence, not for convergence.